Okay, hello everyone, and today's topic is everything you always wanted to know about memory in Python. Actually, this is an extended version of talk that I already gave at EuroPython this year. So there is some new stuff here. Some things about me. I work at Nicolaus Copernicus University. My main interests are mostly databases, GPU computing, data mining, and HPC. And all of this actually require to maintain a large sets of data. I also have, I think, 8 years of Python experience, and I've actually done some projects with Python. And I listed some of them, and they are here on purpose because all of them were actually long-running processes with a lot of memory consumption and a lot of computations. And this one's my main motivation to look out at the Python memory model, because, for example, this simulation was happy with 32 gigabytes of RAM and 6 hours of computation, so I had to try to optimize the memory usage to get it true. Okay, so we'll start with some basic stuff. Here you have probably the most boring table from all these presentations, but it is somehow important because before you start to profile your Python memory consumption, you actually have to try to get some rough estimate of how much of the lower bound of the memory that you will use. So actually you should think about all your data representations and what types of data you use, calculate the estimate of such objects in memory, and try to get the lower bound of your memory consumption. And then you can start the process of memory profiling, because if you don't do this, you actually might try and guess what's wrong with your program, but actually it might be perfectly okay. And just because of the use types, you will get a lot of memory consumption. From interesting things, some of types will you will use some memory for a header and some additional penalty for each element in this each element or the size of the data. You can actually get this information from Python using sysgetSizeOf built-in. It's there from Python 2.6, and it will actually return you the size of your in bytes, and it will work correctly with all the built-in types of Python. But if you use it with some third-party tools, you might actually get some wrong information. So just remember that if you use it with pure Python types, it's okay. If you use it with some third-party tools, there might be some problems with that. And actually, this built-in will also count the additional memory that will be needed for garbage collector and any other overheat, and it will use the sizeOf method. And here's some short note that when you use the getSizeOf on a container, you will actually get the size of the container, so the structure of the container, not the data itself. So here you have two examples. They are actually this data here is a lot bigger than here, but actually this getSizeOf will just return the space for the container, not for the data inside. So remember about that, because sometimes on Stack Overflow you get a question why I get a wrong answer with getSizeOf on my data. Okay, here's something about object interning. Here we have, let's say, fun example. And actually, you might encounter questions about the object interning on some advanced Python quizzes, and so probably because of this, it is worth to know it. And as you can see, we have here these two lines doesn't. The only difference is here, so we just add some bigger number here, and we have two of the same lists with different data. And as you can see, we get a different memory measurements for those two lines. And let's talk about what actually happened here. So normally in Python, there's a general rule that when you create an object and assign it, so when you assign something to a variable, you create an object, and this this variable just points to this object. So each time you do something like this, there's an object created and so on. But there's an exception to this rule, and this is the interning of objects. This is actually done for performance reasons, and actually it's quite implementation specific. So this is true for CPython, but we have to test it on other versions of Python to see how does this work there. And the idea is that for often used objects, we will pre-allocate those objects and share the instances between all the assignments. And so we will do this instead of costly new alloc. And here's some two examples. We start with this one. As you can see, I assigned two zeros and mind the semicolon here. And A is B is true, and A is equal B, it's also true. And here we choose some higher number, and we get that A is not B. And this is because those numbers aren't interned, and but also the value is true here. So a little bit more warning about this stuff. It's highly implementation dependent, and this might change in the future. And actually, there was some to some version of Python that the objects interned were a little bit different, and this is actually not documented because of those two above points. And if you want to know more, you should consult the source code. And for CPython and from 2.7 to 3.4, you'll actually get single instance for each integer from this range, single instance for empty strings and strings of length 1, and the same for Unicode, and also for empty tuples you also get a single instance. Here's something different. It's called string interning. It's designed for interning but only string objects. And we start with something simple. We create two objects, assign them, then we do some. We add something to A and check if it's B, and the answer is of course false. But if we use the intern, it's a built-in. We actually will get true for those two. And following the next example, we here create a list of pretty similar strings and try what's the memory consumption for it, and we actually will get something like this. And if we use the intern, we will actually intern some of the strings, so put them into string intern table, and we'll get a little bit less memory consumption. So let's talk about the string interning in details. So this is let's say it's a common technique in many programming languages. So actually, string interning is representing, if we have the same strings, we can represent them as one object in your program. So actually in Python you got in two dot versions, and in 3 dot versions you get the inter and sysintern versions. Wow. Sorry. Okay. And actually, what this will do will actually, when you use the intern, it will put your string into the intern string table, and if there is a string that is exactly the same in the string intern table, you will get the reference to this string, and in other case, this instance will be created, and you will get the reference for this instance. This is used for performance. You can gain a little performance on dictionary lookup when you use a lot of dictionaries with the same keys. And Python actually uses this internally, so all names in programs are automatically interned, and actually the dictionaries holding the module or class attributes will also be interned. And so you can use this knowledge if you, in particular case, when you have a lot of dictionaries with the same keys. But here's a little bit warning: it's not free. Actually, when you use an intern here, the time will increase. And also, as you can see, I created here a lot of unique strings. So there won't be a memory decrease, because we'll actually have to store all the unique strings plus the string interning table that will grow when we add another string to them. So remember about that. Okay. Now something more advanced. In Python, we have different types of mutable containers. So actually, you get lists, dictionaries, and so on. And there is some allocation strategy for all of these types. And actually, the strategy is that each of these mutable containers will slightly overallocate memory just to gain a little, well, maybe not little, but just to gain the performance. So they are designed to leave room to the growth of the container, and they will shrink only if some threshold is reached to reduce the costly functions like reloc and memcopy. And they will use, of course, the optimal layout. So let's talk about lists, sets, and dictionaries. We start with the lists. So this works as follows. Here we put one element into an empty list, and this will immediately allocate a list for space for 4 more elements, and then we can use those elements later. When we reach the upper bound of this container capacity, then we reallocate and create a wider space for this container. So the lists are represented as fixed array of pointers. They will overallocate for list growth. So actually, it will be something like this when you create a list for some elements. So it will first start with 4, and then it will allocate place for 8 elements, and so on. For large lists, it will be less than 12.5% over allocation. But if you have a lot of small lists in your code, just remember that for 1, 2, and 5 elements, you have a lot of over allocation. Okay, so because of the memory action involves, some operations on a list are cheap, and so on, some are not. So if you put an element at the end of the list, you will actually use a cheap operation because the list is prepared for next element. So it will be pretty cheap. But when you put something into the middle or the beginning of your list, you actually have to do a memcopy, memshift, and sometimes reallocation, and this is costly. And this is the general pattern of how to estimate the size of your list depending on the architecture, and it will shrink only when the list size is less than half of the allocated space. And you can of course use the sysgetSizeOf to get those values. As you can see, we start with an empty list, then we put one element, and the list allocates actually over allocates, and it's prepared to get three more elements. Then it's when the capacity is reached, we over allocate again and again. Okay, for dictionaries and sets, it's actually a little bit different. They are represented as fixed length hash tables, and they actually will over allocate only when you will reach the 2/3 of capacity. And depending if it's a small dictionary, it will be a quadruple over allocation, and if it's larger, then we will only double the size. So you can search the Python code for those elements. And the shrink code, this is actually growth shrink code. This is the for that is done for estimating the new size of the dictionary that you will use. And the shrinkage of the dictionary or set is only done when there is a large amount of dummy elements and compared to number of real elements. So then the shrinkage will be done. Okay, so let's talk about various data representations. You can actually, let's start with some task. We have data that it's described by, let's say, 8 fields, and we know that these fields will get some different values. And how we can represent this data in Python. So we have a lot of possibilities. We can use old style classes only for Python 2.0, or we can use new style classes, or we can use new style classes with slots. I don't know if a lot of people know the slots, but it's pretty useful. But we can do it slightly different. We can use a named tuple, which is from collections, and actually you can just put the names and the data there. You can use, of course, tuple data and store the field names somewhere else. You can use also lists or dictionary data. So the question is how those representations will affect our memory usage. So actually, here's a test for Python 2 and Python 3. And as you can see, actually old style classes and new style classes are pretty expensive, but for Python 3 it's a little bit better. Dictionary is the second of the most memory. We'll use the second that will use the most memory, and then we have the simple types that will actually allocate a little bit less memory. But the winner is actually the new style class with slots. We can get a pretty decent memory representation. And I repeated this for stackless Python, Python 2.7, PyPy, and Jython. Of course, Jython is the worst here, but as you can see, for new style classes, stackless Python and Python are, I think that they are the best here. But PyPy gets a good representation using new style classes without the slots, so it's pretty nice also. Okay, so different topic, garbage collection in Python. So, okay, as you all know, we have a garbage collection in Python. We use reference counting for garbage collection. Actually, Python offers a cycle detection, and we'll talk about it a little bit later. And actually, we'll garbage collect the object when the counter goes to 0. And the question is when we increment and when we decrement. So each of these for example, each of these operations will increment the reference counter, and each of these will decrement the reference counter. So this is pretty obvious, and you all use it even if you don't know. But let's talk about cycle detections and when may it fall. So for example, this is from the Python documentation. When your object, in your class, when you implement the del method, there is no safe way to remove the cycled objects, because we don't know from which object we should start with the del method. So this might be the problem. So let's see example. Here we have a simple class. We create two instances. We create a cycle. We delete them. We use internal garbage collector. We collect the objects, and we examine the garbage that was left, and actually it's clean. So this cycle was pretty simple, and it was straightforward for Python. But actually pretty the same example, but this time with del method, and this time as you can see, there is a lot of garbage that was left behind. So in those cases, you should manually break the cycles and then clean the GC garbage. Some additional notes for Python. Actually, there is no need for a CPython reference counting a garbage collector, because the Python uses Java garbage collection, and in PyPy you actually have a pluggable garbage collectors, and you can choose from, I don't know, 3 or 4 garbage collectors in your code. Okay, so now for profiling tools, we'll start with something pretty simple but pretty useful. So this is the list of tools that I will try to describe. We'll start with time. It's simple but useful, and I'm not talking about the time that you just write, but the user bean time, and with some option, and then you can get some information about your program after it finishes. So like average memory or maximum resident memory, and so on. And actually, you will get something like this from time with minus v option. It's simple, but it's useful, and you already have it on your computer. There's also a module called PUSUtils. It's cross-platform, and it will allow you to check your process during its run. So you can actually ask ask for process information, process dictionary using your PIT, and examine the dictionary that you get, so we can read the memory info, and so on. There's also a tool called, let's say, library called Memory Profiler, and actually it can work in 3 modes. You can use it as line-by-line profiler, you can use it as a memory usage monitor, or use it with Debugger as a debugger trigger. So let's start with line-by-line profiler. Actually, you have to use a decorator on the function that you want to track, and run it with a module here. And then you can get such output that will, for example, show that in this 4 the memory increase is something like that, and you can find the hotspot in your function or something like that. You can also use Memory Profiler as a memory usage monitor. It can work with any program, but if you use it with Python program, you can use the function decorator, and then you can plot the memory usage and also mark the places where each function was called and how it changed the memory usage. on the plot, so you can get such plot. And the last mode is actually the memory profiler as a debugger trigger. You can put a threshold of used memory and run it with the memory profiler. And when you reach the memory threshold, then the Python debugger will be started, and you can look at your code and see what's wrong. Okay, next tool. It's objgraph. It was developed for finding the cycles in your Python code. It will work for simple examples, but when you use it with, I don't know, a large project, probably you will fail, because the graph will be very, very large and it will be hard to investigate. There are some refinement tools implemented here, but you have to know them, and it will take some time to make usage from this tool, but it's worth to know about it. Next, you have two tools. They are pretty similar. They are used for a heap analysis of a Python. You have a Hippie and Melina, and they are pretty similar. Even in the description, they have the references for them. And let's see a sample session with a Hippie. We start with, of course, importing Hippie. Then we start with creating a heap object, and start with creating a heap snapshot. And then we will do some memory intensive operation and do a second snapshot of your heap. Then you can do some simple arithmetics on those snapshots and get results like that. So you see how many integers were created, for example, between those two snapshots. Okay, I will show Melia with combination with run snake run. Actually, you can use them together, and using these dump all objects and then in shell running something like that, you can actually get a pretty graphical interface for exploring your program memory usage. Okay, next tool. It's Valgrind and Massive. Actually, Massive is a part of Valgrind. Valgrind is a programming tool for memory debugging. It's pretty low level, and it's not Python specific. It's C and C++ specific. But you can get a lot of information using it. And here's our recipe. You can use Valgrind. You can always trace childs of process, and you just specify that you want to use a Massive tool, and then your Python interpreter and your code, and you will get an output file with the PIT number. So I've just put this a star here, and you can use a msprint program, which will return something like this. So you'll see in bytes useful heap, extra heap, total, and so on. But also you will get a memory monitor, and you will see how the memory usage was, how is the memory usage in time. There is also a tool called Massive Visualizer, and this actually is developed by KD guys, and you can use that tool to get a pretty decent memory usage graph. There are, of course, many other useful tools. You can actually use Dozer and Dozer for web application development. There is also an option to build your Python in debug mode. If you set something like this, and then you can actually attach a debugger into your process. Of course, there's Valgrind, it was described before, but actually you can use a more advanced option with Valgrind when you compile your CPython. This probably is more advanced because it will turn off the Python allocator, but you can always try it. And there's also a GDB heap. It's a GDB extension. It's pretty low level and still in progress, but you can always use it. Okay, next topic. This is about malloc in CPython. And actually, it's we will start with something low level and about how the malloc works. Malloc has two strategies for allocating new memory. So for small amounts of memory, it will use brk as brk syscalls, and they work like that they can increase the allocated memory size or decrease, but they can only do it on a continuous memory. And for other cases, it will use a more general tool like mmap and moonmap, and this will work for most cases. So the problem is that if you allocate memory using brk and sbrk, after you allocate some memory and then you free some memory and you have something at the end of your memory, you cannot decrease the memory because you still have something here. You can only decrease free memory from the end of this segment. And okay, so this is about how this works, and this can be actually controlled from the programming level, so we can actually set a threshold for when to switch strategy. And here's a warning, and this is important because most of current Python implementations will not be affected. But you can have an old server with some old version of Python, and then you can actually find this problem. So this example is for those cases, but actually current modern implementations of Python are not affected, and actually it also only affected some Linux configurations. For example, on Mac OS X wasn't affected. And once more, it's probably effectively eliminated. But here goes the example. We start with something simple. We have our empty list. Here we will create second list with dictionaries. Then we'll actually remove every second dictionary from this list and put the result into this list. And we'll print the memory usage after this memory consuming operation. Then we'll clean up and print out the memory usage after. And if you are lucky and find an affected system, you'll actually get something like that after the second free of memory, will actually still have a lot of memory allocated. But on most systems, you actually will get a pretty decent result, so the memory actually will be freed. And you can find a lot of blog posts about let's use some other memory allocation tool library than malloc. And of course you can. There are some pros. In some cases it will drastically improve the memory usage of your process or actually improve the performance. But actually it may work against you, and there are cases that using the tcmalloc or libtcmalloc will create more problems than you had at the beginning. And to use them, it's pretty easy. After you install them, you actually have to just set the ld preload variable to the path of your library, and then run the Python interpreter. And there are some things to keep in mind before you use it with Python. They will change drastically the way the Python process will allocate memory, and you have to actually check a lot of things before you decide that okay, we are going with different allocator. So please use checkpoints at various checkpoints in your code. Check how much memory you used at those checkpoints. Check the minimum and maximum memory consumption. Tomek here had example where the maximum usage of process actually increased compared to simple malloc, and but the results was that the process freed more memory. And compare the performance because it can also drop. And here are some results. I did several checkpoints and checked the memory usage at different checkpoints. And actually you can see that this system wasn't affected, and actually I got a pretty decent job done by malloc. And gemloc was pretty similar, and tcmalloc actually did a worse job in this case, but it might be other case in your situation. So in summary, I think that it is important to understand better how the Python memory model works and take it to your adventure. You should pay attention to hotspots. There are several profiling tools, use them. And this is the hardest thing, seek and destroy, so find the root cause of your memory problem and try to fix it. Sometimes it will be difficult, so here are some quick and sometimes dirty solutions. You can always delegate memory intensive work to other processes by using processing and so on. You can of course restart your process regularly or go for low-hanging fruits like slots or different allocators. And actually I think that's all. Here are the references I used. Thank you.
Are there any questions?
I have two notes about your talk. And one question first. Did you see changes in Python 3.4?
Yeah, actually, I know that, as I said before about this example with malloc, it does not affect modern Python's CPython.
Yeah, so. Okay, but there are two things. First, del problem is solved in 3.4, and other there's a trace malloc library, which is very, very nice. Rather simple, but its functionality provides snapshots and trace back to every allocation, so it's nice to use.
Okay, actually tomorrow we have workshops about this with Tomek, and we'll cover this topic also.
I see. Okay, that's all.
Okay.
Do you know any memory profiling tool that's aware of threads and can distinguish between them in the logs?
Actually, I think that I think that you can trace childs with Valgrind. I don't know if it distinguishes them, but you can do it with Valgrind. It's okay.
Any more questions?
So string interning looks really awesome, but can you actually free memory used by intern strings?
I think you cannot. Actually, you will. So this example here I showed. Yeah, here. Actually, here you will grow your string interning table, and I think that you cannot free it.
So it doesn't look like a general solution to the problem of having.
So this warning was to discourage any usage of string interning as a general solution.
Thank you.
Any more questions? Okay, so thank you.
Thank you very much.